Last year in Physics 20, we covered a law called Newton's law of universal gravitation. We found that every two objects with mass exerted a force of gravity on each other. There was a force of attraction on each other. In fact, last year, if you were in my class, remember we did that corny little demonstration? Look at your partner, repeat after me. Remember that one? There's a force of attraction between every two objects with mass, whether we're talking about the Earth and the Sun, or whether we're talking about you and the person sitting beside you. Now, the force of attraction between you and the person sitting beside you is very, very small because, relatively speaking, your mass is very, very small, but it's there. When we talked about Newton's law of universal gravitation, we addressed an experiment that was performed that found the value of G, that constant that goes with that equation. It was called the Cavendish torsion balance experiment. Today we're going to talk about another experiment that's real similar to that one that we talked about in Physics 20. It's called the Coulombs torsion balance experiment, named after a guy named Charles Augustin de Coulomb, who performed this experiment. Here's the basics of it. And if you have this little sense of deja vu as we're going through it, it's because we did something almost exactly the same last year in Physics 20. Here's the ceiling or the top of a box or something. Hanging from that is a string. On the end of the string is a rod. And on either end of the rod are two objects with the same mass so that this balances. We're going to call the first object object number 1, and the second object we don't really care about. It's only there for symmetry to balance it out. Object number 1 will have a charge. How much charge right now doesn't matter. It's going to have a charge, positive or negative. We're going to bring another object nearby that we're going to call object number 2. It's also going to have a charge. What's going to happen as a result of charge 1 and charge 2 coming nearby each other? Yep. Yeah, you're going to get a force of repulsion or attraction between the two. So in other words, number 1 will swing away from number 2, or number 1 will swing towards number 2. We don't really care what happens. Okay, as long as there's a force of attraction, that's all we really care about. Now, Coulomb wanted to find the relationship between these charges and the distance that separates these charges and how they affect the amount of force that acts between these charges. So we performed this experiment, this torsion balance experiment. In fact, he performed it with three different parts. In the first part, he would have manipulated the value of, we'll say Q1. Q is a symbol for charge, right? So he would have manipulated the value of this charge. Responding to that would have been the magnitude of the force. Now, how would he have measured the value of Q1? Well, he couldn't measure directly the value of Q1, but he could measure the relative value. If he has a value of Q and he touches it against something that's neutral, it becomes a half Q. If he touches it against something that's neutral again, it becomes a quarter Q, and so on. He can change the value of Q without really knowing what the value of Q is. It just becomes a half and a quarter and an eighth and a 16th and so on. And he's changing the value of Q without really knowing what the value was before. How does he find the value of F, the force? That's a bit trickier. The value of force is determined by the twisting or the torsional properties of this string. How many people have ever been on a swing set where you sit on it and then you try to turn it around and twist it around? And then once you can't do it anymore, you let it go. But you keep twisting it as long as you can, right? Because you want to go as fast as you can as you're going to let it go and swing around. You guys know that the more you twist it, first of all, the faster you go. But you also know that the more you twist it, the harder it becomes to twist. That's the torsional or the twisting properties of that chain that's on that swing set. If Coulomb knows the twisting or torsional properties of the string, in other words, he knows that if it makes this much of a turn, it required this much force, then he can determine how much force was present when he brought charge 2 nearby charge 1 simply by measuring how much the string twists. He's using the twisting properties of the string to measure the force. Just like in a spring scale, we would use the stretching properties of a spring to determine how much force we had. So when he performs this experiment, measuring or manipulating the value of Q1, measuring the value of F that responds to that, he has to keep Q2 and R, the distance that separates them, constant. They're control variables. You can't go and change Q1 and Q2 and try to find the relationship between Q1 and F. When he does this, by the way, he gets a straight line. That tells him that F is directly related to Q1. As Q1 goes up, F goes up. If Q1 goes up by a factor of 3, then F goes up by a factor of 3. If Q1 goes up by a factor of 16, then F goes up by a factor of 16. They're linearly related. They're directly proportional. Well, then he performs another experiment. This time he manipulates the value of Q2. And responding to that is the force. You've got to keep Q1 constant and the distance separating them constant. Once again, he gets a straight line. This time he finds that F is related to Q2. As Q2 goes down by a factor of 2, then F goes down by a factor of 2. They're linearly related. Finally, he manipulates the value of R, the distance that separates the charges. See how that affects forces. He gets a line that curves downward like this. By the way, what would we hold constant here? What would be my control variables in this experiment? Q1 and Q2. This time he finds the relationship is not a linear relationship at all. This time he finds that it's inversely related to the square of the distance. As R goes up, F goes down. If F is related to Q1 and related to Q2 and inversely related to the square of the distance, then we can put those expressions together or those relationships together and say that F is related to Q1, Q2, and the inverse of R squared together. But if you know anything about proportionalities, F is related to this, but it's not equal to this. If it's related to this, then it's equal to that times a constant that we're going to call Coulomb's constant. The value of that constant is 8.99 times 10 to the 9 Newton meters squared per coulombs squared. R, of course, is the distance that separates them, measured in meters. Q is the charge measured in coulombs, and F is the force of attraction or repulsion measured in newtons. Anybody having a little bit of a sense of deja vu with this? Like, does anybody, who remembers that experiment that we talked about in Physics 20? Just a little bit, yeah? Who thinks that this equation looks familiar? What does it look like? Sorry? Yeah, it looks like the equation that we had for Newton's gravity, which said F is equal to G m1 m2 over r squared. It looks a lot like it, right? They're clearly similar in their structure. They're both what we call inverse square relationships, because the force is inversely related to the square of the distance. It's both a constant times something. What's different? Well, one uses masses, one uses charges. One is a constant called K, one is a constant called G. What do you notice about those two constants, by the way? You anybody remember this one? Good. 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. 10 to the 9 and 10 to the minus 11. The electrostatic force is big. Gravity is a weak force. We think of it as a strong force, but it's not. It's a weak force. The electrostatic force is about 10 to the 20, all other things being equal, about 10 to the 20 times bigger than the force of gravity. Electricity always wins over gravity. It's always a bigger force if there's any charge present, right? If it's not a neutral object. This is just a little table that compares the two of them here. Now the relationship, for both of them, it's an inverse square relationship. The magnitude, well, Coulomb's law is big, and Newton's gravity is small. What about the direction? This is kind of weird, kind of different. Newton's is always attractive, right? Because you don't only have one kind of mass. Somebody in the last class asked about antimatter. Well, antimatter isn't opposite mass. Antimatter is just same mass, opposite charge. No. So it's like you got an electron that has a mass of 9.11 times 10 to the minus 31 and a charge of -1. A positron, the antimatter equivalent of an electron, would be same mass, 9.11 times 10 to the minus 31, but positive charge. So it's not like it's opposite mass. It's not like the force is going to be a repulsive force of gravity here. Okay, gravity is always attractive force, whereas electric force can be attractive or repulsive. We've got one kind of mass. We got two kinds of charge, which can give us that attractive or repulsive force. Let's have a look at an example here. This is a metal sphere with a negative charge. Negative charge. I'm going to circle that actually. Positive charge down here of 1.5. Distance between the centers of these spheres is 3.3 centimeters. What's the magnitude of the force? And what's the type of force, attractive or repulsive, that these two charges exert on one another? Let's write down some givens here. We know that the first charge is negative 2.10 times 10 to the minus 6 coulombs. Second charge is positive 1.50 times 10 to the minus 6 coulombs. Somebody in the last class said, does it matter which one we make Q1 and which one we make Q2? What do you think? No, it doesn't matter. Okay, 1 times 2 is 2. 2 times 1 is 2. It doesn't matter what order we multiply two numbers together in, we get the same answer. If we say 2.1 times 1.5, we get a certain number. If we say 1.5 times 2.1, we get the same number. So which one do you make Q1, which one do you make Q2, doesn't really matter at all. We're going to make R, the distance that separates them. I'm going to make that 3.30 times 10 to the minus 2 meters, or 0.030 meters. And I want to find the force. Now remember that the equation is only going to give me the magnitude of the force, not the direction. I'll have to find the direction some other way. F is equal to K Q1 Q2 over R squared. As I go through this, I'm going to try to trick you. But I'm warning you right now that I'm going to try to trick you. Okay, let's see if you can pick up on it. The value of K is on our data sheet. It's 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Q1 is 2.10 times 10 to the minus 6, and Q2 is 1.50 times 10 to the minus 6. The value of R in meters, 3.30 times 10 to the minus 2. And we can't forget to square that. What's our answer? I think it works out to be 26. 26.0. What am I trying to trick you with? Yeah, Ethan? The 2.1 should be negative. Oh, there's the trick. The trick is that everything up on the board is correct. The trick is that you don't put a negative in there. Now, why not? Let me preface this, actually, the answer to that question, by saying that in some textbooks that you'll read, some suggest that you don't put a negative in, some suggest that you do put a negative in. The good ones suggest that you don't put a negative in. Why not? Well, yeah, it's an absolute value, the way that I have the equation written. If we were to put the negative sign in there, then we take off that absolute value. But you're right, the way that I have it written, absolutely, absolutely. Yep. Exactly. Listen, for us, negative means direction. We don't want to start mixing and matching sign conventions. You can plug a negative in there and say, like, okay, it means negative, whatever. But we don't want it to mean negative charge. We want negative in an equation to mean negative direction. You start mixing and matching those sign conventions, and you're going to end up getting confused. Probably not so much on this question, but on questions that we're going to do over the next couple of days, you will start getting confused. So, drop the sign of the charge. Always, when you're plugging into an equation, drop the sign of the charge. There's the magnitude of the force. Somebody tell me whether it's attractive or repulsive? How do you know it's attractive? Good. we still have to use the fact that one's positive, one's negative, because that's what tells us whether it's attractive or repulsive. But we're not plugging them into an equation. We know it's an attractive force because they're opposite charges. All right? If they happen to be like charges, then they would be repulsive. All right. Have a look at this question, please, on page 530. Let's take a look at one more here. Since the two spheres in example 10.1, the last one, are momentarily brought into contact, then return to their original separation distance. So these guys, these guys in this example are touched and then brought back to the original separation distance. We want to find the force. How is this question any different than the last example we did? Right? Yeah, exactly. They balance out, right? So they started off as negative 2.1 and positive 1.5. But when they touch each other, what do they become? 2.1 and 1.5 gives me negative 0.3, or 3.0 times 10 to the negative 7. Is that right? I think that's right. 3.0 times 10 to the minus 7. All right, now we want to find the force that acts between them. It's going to be different, right? Because the charges are different. KQ1, Q2 over R squared. K is 8.99 times 10 to the 9. Q1 is 3 times 10 to the negative 7. Q2 is 3 times 10 to the negative 7. And R is, I forget what it said R was, 0.033. So figure out what that is now. 8.99 times 10 to the 9 times 3 times 10 to the minus 7 times 3 times 10 to the minus 7 divided by, use some brackets on the bottom here, 0.033 squared. We get 0.743. Now, if we wanted to express that as a numeric response question, it would either be scientific notation A decimal B C times 10 to the D, or B times 10 to the W. This would be 7.43. This would be, no, sorry, this would be 7431. And this would be 7.43. All right, try this one. In this question, we got to recognize that they touch, and then we want to find the force. Then separates the question into really two separate questions. They touch a negative 3 microcoulombs, a positive 2 microcoulombs. When they touch together, they're going to balance out to be what? Negative 3 microcoulombs plus positive 2 microcoulombs divided by 2 gives me, is that negative 1, negative 0.5, or negative 5.0 times 10 to the minus 7 coulombs. That's what each of them become now. Q1 was 3 microcoulombs. Now it's negative 5 times 10 to the minus 7. Q2 was 2 microcoulombs. Now it's negative 5 times 10 to the 7. Well, now we're going to say F is equal to KQ1, Q2 over R squared. And we got K is 8.99 times 5 times 10 to the minus 7. Drop that sign, right? Drop the negative. What did I just do there? What? Oh, what is it? Yeah, I just saved a little bit of writing, right? I ran out of space. I saved some writing there. 5 times 10 to the minus 7 times 5 times 10 to the minus 7 is same as 5 times 10 to the minus 7 squared over R squared. And R is, what is R? 0.12 meters, or we could say 1.2 times 10 to the minus 2. Don't forget to square that. Let's do the math. We get 8.99 times 10 to the 9 times, I'm going to use some brackets here, 5 times 10 to the minus 7 If you're not comfortable with squaring that because of the exponent, then just multiply them together. 5 times 10 to the minus 7 times 5 times 10 to the minus 7. Divided by 0.12 squared, we get 0.156, or 1.56 times 10 to the minus 1. How do we know that it's repulsive, as they tell me here? Yep. How do we know it's repulsive? Yeah. Yeah, like charges are going to repel each other.